Okay, so we kind of looked at some relationships between pressure and volume and density. And now we're going to look at kind of what happens if we're like pushing fluid through a system and we're adding velocity into it. Okay, so for you guys for this class, you are just looking at fluid dynamics in terms of like, we're modeling like these ideal fluids. So ideal fluids, we're looking at I think that you actually do have some problems like where you have viscous fluids. So if you see that term, things will behave differently. So I would check your book kind of for the last section for there, but we're going to look at ideal fluids are non-viscous, they're steady, incompressible, and we're not dealing with any rotation. We're just pretending that they're going like kind of perfectly, smoothly straight through um, any kind of surface or barrier, basically. So, okay. This is kind of like sort of a diagram here where we would say like, okay, so we have a fluid, we've moved some distance delta x over here, we have some velocity of the fluid here, and it's coming through a different cross-sectional area, right? It's traveling this distance like delta x2, and it's coming out. So what we're saying, so these are velocities here. Okay, so we're saying this cross-sectional area 1, so this would be the cross-sectional area, 1 times the velocity 1 is going to be equal to the cross-sectional area 2 times the velocity 2, the external velocity. So we're relating these two and basically saying like the speed which it like crosses one cross-sectional area is going to be related to the speed that it crosses like the other. Okay. I think maybe I should draw this over here, but I think it looks a little better there. Okay, so all right, let's do kind of an example for a couple of these. So okay, we have a Niagara Falls example. So it says each second, all of this water falls over a 670 meter wide cliff for Niagara Falls. So this is 670 meters, and this is how wide that cliff is. And we have water that's coming over the cliff. Okay. And we also have a depth of the water. So it's 2 meters deep as it reaches the cliff. So 2 meters deep for the depth. Okay. And the question is, what's the speed at the instant that it reaches the cliff? So is what. So in this case, we know that if we have if we just take our area, so we want to look at the area of the cross-sectional area of the water. So this is that kind of cross-sectional area that we talked about, right? So the water is going through this this cube surface here, right? Or this rectangular surface. So let's say the area is equal to 670 meters, right? Times 2 meters. So just this width, right? Times the depth of the water. And then we want to look at, so we know how much water, right? This is how much our volume is here. And so in order to find the, let's see, oh, sorry, each second. So we have a flow right here. So we have 525, or 5525 meters cubed, right? And then we know that this is per second, right? So we actually, to get the velocity, these units are weird. We want meters per second for our velocity, right? So this problem basically just gave us some flow rate here for like the volume of water per second. So let's figure out how quickly it goes by basically taking this flow rate that they gave us, so 525 meters cubed per second, and we're going to divide it by meters squared, right? We're going to divide it by the area, meters squared, so that we can get meters per second to get our velocity. Okay, so in this case, the velocity of our water, this is just sort of an algebra thing, where it's going to be equal to 4 meters per second if we plug in all of our values here. So if we plug in our area is equal to 1340 meters squared. Okay, So this is just kind of like a conceptual look at like how we are measuring the fluid going through a cross-sectional area. Okay, so in the second problem, this one's actually very similar to the homework. So there is a garden hose. We're given a diameter of the hose, and they're using it to fill a bucket. So the gardener notes that it takes 1 minute to fill the bucket. The nozzle has this cross-sectional opening, uh, and that's what's attached to the hose. So the nozzle is held so that the water is projected horizontally from a point 1 meter above the ground. Over what horizontal distance can the water be projected? Okay, so this is kind of a two-part problem. And I kind of want to give you a chance to maybe try this one. So this is using two things here. The relationship between the area and the velocity, okay? And then also at the end, there is a projectile motion problem where they want to figure out over what horizontal distance can the water be projected. So for the projectile motion part of the problem, this is kind of a pain, but basically, so if you find the vertical distance and use that to find time, and then if you look at this guy, and use this to find your horizontal distance, we can relate kind of those things there. So I will go ahead and pause and kind of give you a chance to approach